Okay, the next section is on solution concentration and stoichiometry. We want to look at the solution concentration in particular because it so happens that most chemical reactions are actually done in solution. That is, with the reactants dissolved in water. And when the reactants are dissolved in water, that's known as an aqueous solution. And we've seen already that you use AQ in parentheses after the chemical formulas to denote that they're dissolved in water. And just as a reminder, a solution is another word for homogeneous mixture. A homogeneous mixture is a mixture in which the various components mix evenly within any given sample. So like salt water is a homogeneous mixture where it's equally salty at the top as it is at the bottom. But the composition can still vary from one sample to another. So, some salt water could be more concentrated than another sample of salt water. And any solution is made up of at least two components. And one would be what's known as the solvent. The solvent is whichever component is present in larger quantities. In the case of aqueous solutions, the solvent would normally be water. And also one or more solutes. The solutes are the stuff that's dissolved in the water, whatever's present in smaller quantities. There can be more than one solute. For instance, in a saltwater solution, you could say that the salt is the solute, but when you dissolve sodium chloride in water, it actually splits up into sodium ions and chloride ions. And so there are actually two solutes in salt water, sodium ions and chloride ions. And they're both dissolved in the water. So you got one solvent, two solutes in that case. We're interested in this because, again, that's the way most chemistry is done. And so we need to know, in order to be able to do reactions where the reactants are actually dissolved in water, we want to be able to still evaluate how much of each reactant there is. And in order to do that, we have to have some idea about the concentration of solution. The concentration of solution just gives the amount of solute relative to the amount of solvent or the whole solution. And that way you can actually find out, say, how many moles of one or the other reactant you have, if you know what the concentration of the solution is and how much of the solution you have. So the concentration gives the amount of solute relative to the solvent. Or solution. And there are several ways to measure it. I underline solution here because the most important form of concentration that we use in chemistry, in fact, actually relates the amount of solute to the amount of the entire solution rather than solvent. And so that's a relationship that we're going to see quite a bit. The amount of solute can vary. The amount of solute can actually vary from one sample to another. And a small amount, relatively speaking, and these terms are sometimes kind of arbitrary, but relatively speaking, a small amount of solute would be a low concentration, and that would be a dilute solution, while a large amount of solute would be a concentrated solution. The most important form in which we express concentration in chemistry is known as molarity. And the symbol for molarity is a number followed by a capital M. And molarity gives you the number of moles of solute divided by the volume of the whole solution in liters. And so in terms of units, molarity can be thought of as a unit in itself, but it actually stands for moles per liter. Okay. When you want to make a solution of a certain molarity, what you would have to do would be to calculate how much of the solute you need for the solution, and you would put that into what's known as volumetric glassware. That's some laboratory glassware that's capable of measuring volumes very accurately, and basically fill up the volumetric glassware until the total volume, that is the water that you're adding plus what was already there, the solute, is equal to the desired total volume. You basically do it that way because the solid solute itself takes up a certain amount of volume. It's usually pretty small compared to the volume of the water that you add to make the solution. But if you want to be accurate, then you need to make the solution that way. You add the solid solute first, and then add enough water to bring the total volume up to what you want the volume to be. An example of an easy calculation involving molarity is what is the molarity of a solution made by adding 45.4 grams of sodium nitrate and adding distilled water. DH2O means distilled water. That's the kind of water that we normally use in the lab because distillation removes a lot of the contaminants that are present in tap water, things like minerals and that sort of thing. And because a lot of minerals that are present in tap water can actually interfere with a lot of the chemical reactions we might want to do. So anyway, adding distilled water up to a total volume of 250 milliliters. So the two things we need here would be moles of the solute, which is the NaNO3, and that would be 45.4 grams. And you go to the periodic table to find the molar mass of sodium nitrate, which is 85 grams per mole. And 45.4 grams divided by 85 is 0.534 moles. NaNO3. And you also need the volume of the solution in liters. The volume of the solution was 250 milliliters, and there's 1 liter for every 1,000 milliliters. And so that's 0.250 liters. The molarity, capital M, that's not very capital. Okay, capital M would be number of moles of solute divided by the volume of the solution in liters, and 0.5334 divided by 0.250 is let's see, three significant figures. 2.14 capital M. And so that would be how you convey the molarity, is just a number followed by capital M. So 2.14 molarity means 2.14 moles of sodium nitrate for every liter of solution, and 0.534 moles in 0.25 liters just happens to be the same as 2.14 moles in 1 liter. So, the ratio is the same. Okay, you can use molarity in calculations, not just for finding molarity, but for, say, if you know the molarity and you want to know how many moles are in solution, or if you know the molarity in the moles in solution and you want to know the volume of the solution. There are all kinds of different relationships. So in other words, you can use molarity as a conversion factor. And I believe I showed the triangle that you can use for three-term equations. Let's make that bigger. Before, when we were working with density. Anyway, if you have an expression like molarity, which is equal to number of moles divided by the volume in liters, you can actually write it in a triangle like this with three spaces in it. And if molarity is number of moles divided by the volume in liters, you can write the square like this, and basically whichever one of these three terms you want to find out, you cover that with your finger and it's equal to what's left. So molarity, capital M, is equal to number of moles of solute divided by the solution volume in liters. If you want to know the volume in liters, that's number of moles divided by molarity. If you want to know the number of moles in solution, that's molarity times the volume in liters. And so just by making this up, you can find out the relationships between those three quantities. Also, you can keep an eye on the units. In fact, you should keep an eye on the units anyway, because if you, like I said, if you make sure the units come out correctly, then the number's probably going to come out correctly. And also, a lot of times if you forget a formula or something and you're at a loss, just look at the units of what you're given and piece those numbers together so that the units come out correctly, and the number will probably be correct also. So as an example, what mass of KBr is required to make (250 milliliters) of a 1.5 molar KBr solution? Okay. The equation for molarity does not involve mass. It involves number of moles. So anytime you have a question involving mass and molarity, you're going to have to go by way of moles. So first you want to basically find number of moles required for the solution. Okay, so number of moles is molarity times volume in liters. And remember, molarity is in units of moles per liter. And if you then multiply that by volume in liters, obviously liters are going to cancel and you get moles as your unit. So that's another way to keep it straight. Just think of the units. A lot of times, if you're given a molarity and you have to do something mathematically with it, one of the best first things you can do is rewrite it as explicitly moles over liters. Instead of just 1.50 M, you could write that as 1.50 moles over liters. And that might help you decide what it is you need to do. So in order to find the number of moles in solution, you take molarity times volume. The molarity is 1.50 M. Or, as I said, that also means 1.50 moles per liter. So if you write it like that, it makes a little more sense. What you have to do, multiply by liters. We've got the volume in milliliters, but we just saw that the 250 milliliters is 0.25 liters. And so 1.50 moles per liter times 0.25 liters gives us 0.375 moles of KBr. Now, that's nice, but you're not done yet because the question said what mass, and this is moles. Well, for mass, all you have to do is take number of moles times the formula mass. So if there are 0.375 moles of KBr required, and you find out from the periodic table that the formula mass of KBr is 119 grams per mole, we end up with 44.6 grams of KBr required. Okay, so there's one thing you can do with it. Some other examples. Let's see. You can let's see. You can use molarity as a conversion factor, as I said, between the volume of the solution and the moles of the solute. And you can use this triangle here to figure out the ways the equations should be arranged. Another example might be how many grams of sucrose are there in 1.55 liters of a 0.785 molar solution of sucrose? And sucrose has the formula C12H22O11. And let's see, we need, as above, we need the number of moles of sucrose first. And that's molarity times volume. And the volume doesn't need to be in liters, though. Okay, we have the volume in liters, actually, so that helps. Let's see, number of moles is going to be 0.785 M, and that means 0.785 moles of sucrose per liter of solution times the volume of the solution. Liters of solution cancel, and we get moles of sucrose. And so let's see, 1.217 moles of sucrose. grams of sucrose will then be just number of moles times the molar mass. And the molar mass of sucrose, you go to the periodic table and add up the masses for 12 carbons, 22 hydrogens, and 11 oxygens, you get 342 grams per mole. And that gives us 416 grams of sucrose. All right, that's another example. An example of finding the volume. So how many milliliters of 0.155 molar KCl solution contain 2.55 grams of KCl? Okay, so you took 2.55 grams of KCl. Another way of putting this is we made a 0.155 molar solution of KCl using 2.55 grams KCl. What is its volume? That's another way of putting it. Okay, so let's see, we have grams. So the first thing we'd want to do would be turn grams into moles, because molarity involves moles rather than masses. Okay, so 2.55 grams KCl. And there's 1 mole of KCl for every, or is it 74.5 grams? And let's see, that means we've got 0.03423 moles of KCl. Using the molarity equation, you can find the volume in liters pretty easily. Oh, sorry. So the volume of solution is just going to be number of moles of solute divided by molarity, according to our triangle. And remember, molarity is number of moles of solute divided by the volume of the solution in liters. And another way of saying that would be number of moles of solute times the volume of solution over number of moles of solute, because dividing by molarity is the same as multiplying by 1 over molarity. And you'll notice now that number of moles of solute cancel, and you get volume of solution. So it does work. Now, to actually put the numbers in, number of moles of solute was 0.03423 moles, and the molarity is 0.155 moles per liter. That's what molarity means, of course. And when you divide that out, we get 0.2208 liters. And that's times 1,000 milliliters per liter. That's 220.8 milliliters. Or to be correct in significant figures, that would be more like 221. And that's the number of milliliters. Okay, so that's an example of how to find the volume of solution. Apart from making and reacting solutions, one other thing you can do with solutions is dilute them. Dilution is addition of solvent. Okay, to a solution. The effect is to increase the volume but the number of moles of solute remain the same because you're adding solvent, not solute. And the result of that is that concentration goes down. So dilution has the effect of reducing concentration because concentration is the number of moles per liter or volume of solution. So if the number on dilution is adding solvent. So it has no effect on the number of moles of solute, but the solution does contain solvent, so adding solvent increases the volume of solution. The number on the bottom of the fraction is getting bigger, and dividing by a bigger number gives you a smaller result. So dilution reduces molarity. And we can show that because we know that the number of moles of solute in a solution are equal to molarity times volume in liters. Okay, so the number of moles of solute before a dilution, we'll let that equal M1V1. And we'll call the number of moles of solute after the dilution M2V2. And if the number of moles of solute stay the same during a dilution, that means that M1V1 must be equal to M2V2. So M1V1 is just the moles of solute before a dilution. M2V2 is the moles of solute after a dilution. But because M1 is the concentration and V1 is the volume, they will both change during the dilution. But molarity times volume will still be the same as it was before. So in other words, during a dilution, volume increases and molarity decreases by the same factor. Or another way of saying that is that molarity is inversely proportional to volume. So as the volume of a solution goes up, the molarity goes down. If you double the volume of a solution, you cut the molarity in half. Okay, if you somehow manage to find a way to cut the volume of a solution in half, you'll double the molarity. Or if you're comparing two different solutions with one of them, they have the same amount of solute, but one of them has twice the volume. That one will have half the concentration. One of them has half the volume, it'll have twice the concentration. Okay, so now we can look at dilutions of solutions. This is very useful because in chemistry, we usually keep what are known as stock solutions, which is really concentrated versions of the various solutions that we need for experiments. And that's partly to save room, partly to save money, and we rely on our ability to dilute those solutions as needed in order to produce less concentrated solutions for various reactions that we might have to do. More concentrated solutions take up less room, and it's also much less expensive to have one really concentrated solution and dilute it as needed, as opposed to buying ready-made solutions and all of the different concentrations that you might need for all of the experiments you ever plan to do. So dilution is something that we have to do quite a bit in chemistry. And now we know how to do it. We can relate the final volume that we need to achieve in order to change the concentration in a certain way, or we can figure out what the concentration will be after we dilute a solution by a certain amount. But I see that we've gone to about 30 minutes for this segment, so I'll cut it there and we'll continue on with some examples in part B. Be right